Okay, so it's a landing video. I'm just gonna go ahead and finish part one of the experiment. I got both tea candles still lit. Place these two beakers over, hit start on the timer. Bam, quick, 2.5 seconds. Bam, about 6 seconds. So 2.5 seconds it took for the candle in the small beaker to go out. It took 6 seconds for the candle in the larger beaker to go out. So 2.5 and 5 seconds, 2.5 and 6 seconds. Awesome. Okay, so now I'm gonna finish up part two. You've already done it, so let's see what happens here. So I'm gonna put this empty, inverted, larger beaker over. Of course, the volume is just, the height of the water inside is just where the height was originally in the pie plate, and bam! So interesting, the candle goes out pretty quickly, and the water inside the beaker, as I'm sure you saw, just kind of rise up suddenly. So interesting. So we have two things to explain why there's a time difference for the candle to extinguish dependent on the size of the beaker. That's thing one we got to explain. And then what explains, clearly this is the thing we got, the phenomenon we have to explain, what explains this water just rising up, the water level rising up inside of this larger beaker when you put it over the tea kettle. So let's see if we can try to make sense of these two interesting observations. Okay, so a quick first conclusion that we can draw is that fire changes the properties of air. Now that doesn't sound extremely revelatory or highly intellectual, but if you think about it in terms of the history of humanity, it actually is quite remarkable, because for most of history we have deemed air as an inert, uninteresting, ignorable, unimportant substance, basically just taking up space between solids and gases. But in this experiment, we have seen air take on two different properties. The first property was, in the beginning, the closed system of air was able to sustain a flame, and in the end of the experiment, that closed system of air was not able to sustain a flame. And in fact, if we were able to go and try to relight the candle inside without adding in any new air inside the closed vessel, you would see that you could not relight the candle. So we literally have permanently altered the property of the air inside the closed vessel, and that is in complete contrast to the air outside of the closed vessel, which can basically sustain a flame as long as there's wax. So let's just recall what the theory of phlogiston states, and it states that burnable substances, by definition, have phlogiston in it, and when those burnable substances actually burn, it's the phlogiston that's being released. And so you recall, we know, or the phlogistonists, I just made that word up, believed that wood was made of ash and phlogiston, because when you burned it and the phlogiston was released, ash was left behind. So are these two tenets of the theory of phlogiston consistent with the observations of this results? Well, they can be. Let me see if I can explain. So if you kind of think of air as, and this is what they pictured, as some sort of sponge that can absorb phlogiston being released when something burns. If you have a larger vessel, you can absorb more phlogiston. If you have a smaller vessel, you can absorb less phlogiston. And as soon as your sponge is saturated with phlogiston, no more phlogiston can be released from your burning thing, your burning entity, and so the candle extinguishes. So if you can absorb more, the phlogiston, there'll be more space for the phlogiston to go into, and you can release phlogiston for a longer period of time. So, bam. First observation explained. The theory of phlogiston holds water, standing the test of time. Second observation, water gets sucked up into the beaker. Well, if phlogiston itself is attracted to water, maybe the water sees the phlogiston, or it's connected, it's touching the phlogiston as it's being released, and the phlogiston sort of sucks or grabs up the water. Now this is kind of surprising, because you would think that if phlogiston is being produced, if this element was actually coming out of the candle, it would actually push away water, not pull up water. But this was one of the explanations these early chemists gave for why water was sucked up into the beaker. Some other chemists so almost kind of just refused to address this phenomena and basically just ignored that phenomena in order to preserve this idea of Flightstone, which was so successful at explaining so many things, so much more successful than the old theories. So what do you think? Can we ignore that phenomena? Does Flightstone make sense? Is it holding water? Is it standing the test of time? We shall see.